Okay, this is pretty much review except for on the very bottom. So the numbers though are kind of significant. You know that if k is greater than 1, it means something. It means that whenever you have k, which is concentration of products over concentration of reactants, if it is large, that means you have a large amount of a large concentration of products. That's all. This means the products are favored. So mathematically, it's same. It makes sense mathematically. You do not have to memorize if k is greater than 1. It means the products are favored. If you understand the math. If you care to memorize it, that's all you. I'm not a big memorization person. I try not to. I don't have enough space. There's limited capacity here. Okay, so another way of saying that though is the equilibrium lies to the right, and that just means lies to the product side, or it might be written as something like that with little arrows. Same. All it means the same. If this is the important part, if your k value is humongous, like thousands, then I'm going to assume we have pretty much all products and no reactants, and if that occurs, then we say it goes to completion. So the numbers with the k's are just a little bit more detailed now than our generic, the products are favored. So it's in the thousands, the reaction goes to completion. Opposite of that, very small, means you have a lot of reactants, and then you have relatively few products. Therefore, favors the reactants, lies to the left. K is less than 1, but if it's very less than 1, I'll have that up here. If it's 1 times 10 to the negative, no, I can't even say that. I'm not going to put a value on it because it varies. For example, I'll just give an example. For example, if it's 1 times 10 to the negative 20th, okay, what you would probably say is it's essentially, this reaction does not occur. Essentially, but a tiny bit of it does occur to make that small value of k. For example, KSP numbers are going to be that tiny. Like, give me a precipitate example. Copper 2 nitrate, and all nitrates are soluble. Barium sulfate. Okay, so if barium. I know that was like way too many years ago. So barium sulfate is a solid. When it precipitates out, it actually does just a tiny bit dissolve into the ions, or dissociates into the ions, or dissolves. But it's going to be an equilibrium reaction. So you write your double arrow. What are the 2 ions it dissolves into? 2 plus and sulfate 2 minus, aqueous. So this K value, if that is the K value for this reaction, you would say that very times a million amounts of the ions are going to be existing in solution. But it still happens, even if it's very small. Yeah.
How would you write very times a million? Your response question?
That would be awesome. They would probably laugh at me for that. No, you would just say the amount that is dissociating is negligible. Big words. Okay. Last part down here. And that's what I just, oops, I'm sorry, where'd it go? That's what I just said. It's essentially, well, no, not this one. This one I said is essentially negligible. But when you have k is equal to 1, that means that the reaction is favored both in the forward and the reverse direction. So it exhibits no tendency because neither direction is favored. So that's why it's hard to tell really what's happening, because neither direction is favored. You're not going to see a significant change in either side. K equals 1 does not mean it's at equilibrium. Okay, that is a big misconception. Oh, it's at equilibrium, K is equal to 1. No, everything's at equilibrium if we're talking about K values. We're talking about the K of equilibrium, the equilibrium constant. So don't let that be a misconception either. And just like our rate constants, little k's have temperature dependency, so does this one. And so, because temperature is a big factor in Le Chatelier's principle, so only one value for temperature, one value of K at a given temperature, because reactions can be exothermic or endothermic. And if you change the temperature, it causes a big shift, either shift left or shift right, according to Le Chatelier's principle, which we're going to get into a little bit more later, but it can really affect the position of equilibrium or the value of K. That's the only time you can change K. the equilibrium constant K, is if you change temperature. I don't care if you add a ton of reactants, add a ton of products, change the size of the vessel, beat it to death, I don't care. You're not going to change the value of K. The only thing that changes the value of K is temperature. Okay, and then the last part right here where it says an infinite number of possibilities of the positions or number of reactants, or concentrations reactants, it just means that it doesn't matter, as long as I'm just going to use an example of your lab where you had concentration of B, which is the products, or concentration of A. It doesn't really matter what this number and this number is. It will work itself out, so this K and Q is always constant. So these can be infinite in numbers or infinite numbers, but they will always work out when at equilibrium for the K number to be constant, whatever is designated to be at that temperature. Thumbs up, good so far. I'm not speaking like Spanish anymore, right? Okay. Yeah. Okay, this is the cool part. So just like Hess's law where you flip a reaction, what did you do to delta H? You like turn the reaction around. You switch the sign, okay? This one is really similar, so it's something you're kind of familiar with, that you can manipulate the values of K when you manipulate an equation. It's just not exactly the same as Hess's law. So you already wrote that down, that's cool. This is what you read about in your introductory reading, pages 1 through 7. When you flip a reaction, reverse a reaction, the KEQ itself is quote-unquote reversed. It means inversed, okay? 1 over K, or K to the negative 1 is how it likes to be read. If you multiply all the coefficients by 2, or reactions multiplied by 2, that means the coefficients themselves are multiplied by 2. So if you remember, for a reaction, it's C to the C power over B to the B power. I'm just making up examples here. If I multiply the coefficient by 2, essentially that translates to an exponent being changed when you go to the equilibrium expression. So that's why you have to square KQ and not just multiply KQ by 2, because in your in that reaction right there, it's like B yields C. For my like hypothetical reactions here. So your B and your C are your coefficients of reactants B and C. So those get transposed to exponents, and so if you multiply all your coefficients by 2, then you're essentially multiplying your your exponents by 2, which means you're squaring them. So that's why it's K squared. And then if you have multiple reactions and you add them together, you're going to then pull your K's together in a special way. They have to be multiplied, though. They are not added like Hess's law is added. They're multiplied. So it's a little different, but it's a similar concept. So multiply your K's together. And fun fact, K has no units. Yeah, you know units. Little K rate constants definitely have units. I'm watching you. Has little, they do have units, but big K has no units. So yay for no units. Occasionally in life, it makes us happy. Okay, and it's because the rate constants, rate K constants cancel each other out. Their units cancel each other out. So there were units, but thank God for cancellation. Okay, so we have a reaction where we have dinitrogen tetroxide colorless, which makes that nasty poisonous brown gas, nitrogen dioxide. What is the case? What does the Kc just means? When I put C, I just mean related to concentration. What is the Kc expression? Concentration of NO2
over concentration of
Okay. How does it change when I go from here to here? All right, so the reaction flips, so what happens to the K? It's inverse, okay? So I'm just going to take it and just switch the numerator and denominator. So concentration of N2O2 to the 1/2, O4, sorry, and then NO2. All right, so it's not really that bad. It's just learning how to manipulate. For the next example, okay, for the next example, they're actually giving you the actual values. So given these following equilibrium reactions, calculate the Kc for the following reaction. Can't put this on the same page, isn't it? Okay. So what do you see that is similar between these? The first two reactions.
They're the same.
No.
If you Oh, H2HO.
Alright, so when you add them up, you're going to be canceling left and right like Hess's law allows you to. That's an appearance something on the product, and the reactant side can be negated. So you can see that those two things are similar. Okay, so then when you sum them, you see this equation, yes? Okay, so when you sum, check two of those guys and oxalate. Okay, so what am I supposed to do with the K's? Multiply, thank you. You add the BCEs, but you multiply the reactions. The K's. So then you would just take 6.5 times 10 to the negative 2 times 6.1 times 10 to the negative 5. Marker's not liking me. There we go. Yeah, I'm not doing that in my hand right now. But you guys see the point. You manipulate it a little differently than thermochemistry. Are we okay? Okay. Keep talking to me. I need to hear your voice. Okay. Okay, so this is the fun part. You can do Kc and Kp together. Kc refers to concentrations. Kp refers to partial pressures. They are not interchangeable. They are not the same thing. They are still, yes, an equilibrium constant for a given reaction. But if you have the concentration of a gas, it is not going to be exactly the same number as the partial pressure of that gas. So therefore, they are not interchangeable. But you have a formula to help you interchange them if you ever have to convert to and from. And it's called the politically correct formula. You remember reading that? Mm-hmm. Politically correct. Okay. So I'm going to shoot down here first, and I'll come right back up here. Well, I'll show you this first. So there, since the equilibrium pressures are partial pressures are what we're dealing with at equilibrium, they are proportional to the concentration, so they're similar. They're like directly related. Increase in concentration should increase pressure, but they're not interchangeable. They're just related. So this is going to be related to concentration because it's kind of like moles of gas per liters of gas. So as the concentration goes up, the partial pressure will go up. So you can definitely say there's a relationship, but they're not interchangeable. So when you do that, you can set up whenever you put the equilibrium constants together and relate them, you relate them through this formula. It looks really, really, really similar to P equals nRT. Okay, so here's your P, and then N for concentration, RT. However, we have this weird exponent to the delta N of the gas. And this one I remember is the politically correct formula because it's always P first and C second. So politically correct. The only thing that's different here is that we have to know how to calculate the delta N. N refers to, remember, okay, so the change in moles of specifically gases. I don't care about solids or liquids or aqueous. I care about gases only. Because gases are always going to be causing pressure, and so that's why you have to refer to only gases. Because the solids, liquids, aqueous, they won't be causing pressure, so there's really no use for them in trying to correlate to partial pressure because they don't cause it. So you have to take the moles of product gas minus the moles of reactant gas to get that delta N. Still same thing, products minus reactants. That's not like a surprise as to that occurring. And we'll do an example with this too, or like a couple of examples.
So your Kc zero is overvalued?
Your Kc will usually be a given value, given like it's a number. You're not going to actually calculate it. It's going to be given. Well, you're not going to calculate it like this. Okay, that's just showing the direct relationship. That really has nothing to do with your Kc. Your Kc is still concentration of products or concentration of reactants.
Okay.
But if you're given a Kc, you can then calculate the Kp for that reaction, just through this formula. R value is still your one with atmospheres, 0.0821 atmosphere liters per mole K. Okay, and tell me if I'm right. Did I print off you guys some stuff based on this? Let me see your like first or second page. I did. Yeah. Yay, Enlo. Oh goodness gracious! I should have told you to pull that earlier. It's there for you in case you want to go back. It's the first upper left hand side corner.
It's like the first page.
Sorry, I forgot to tell you I printed that. Sometimes I forget what I printed. But this is printed, so you can write on your paper or at least look at it on your own paper. I'll do like maybe 2 with you, and then you guys got this. So for Kc and Kp, consider the equilibrium shown, blah, blah, blah. Write the expression for Kp for this equation, for this equilibrium. Go for it. Kp equals, no,
First K
Thank you. P, partial pressure of, yeah, go for it.
SO3 squared.
Okay. Oh, I'm sorry. What was the next one?
Partial pressure.
Oh, we choose the first. Thank you. I say it like that because it really makes you remember, like, oh, I can't say concentration, it's a pressure. I have to say partial pressure. So you just have to make sure that you can read between the lines. All right, so that's pretty easy. Write the Kp for the reaction shown in 1A above. Oh, sorry, the Kp is 0.25. Determine the value for the Kp of this reaction shown. So if this reaction has a Kp of 0.25, what's different? It's
1 over.
right. So if the reaction is reversed, you invert your K. So that's 1 over K, which is 1 over 0.25. No calculator. What is it? 4. Thank you. How many times does a quarter go into a dollar? 4 times. Good. All right. So that one is 4. So according to your knowledge of K's, which reaction is more favored towards the product? First or second? Definitely the second because it's greater than 1. The first reaction, the way it's written anyway, is more favored towards the reactants. Okay. At a particular temperature, 1.25 liter flask contains that many moles of hydrochloric acid, that many moles of hydrogen, that many moles of chlorine. All species are gaseous. Determine, so these are your important numbers. Moles of HCl, moles of hydrogen gas, and moles of chlorine gas. So if I were you, I would be writing down my givens, which are those 4 numbers. All species are gaseous. Determine the Kc for the formation of hydrochloric acid at this temperature. So far you've written down your V, volume equals 1.25, your moles, your moles, your moles, and then now we have to write down what? Bc. So formation of HCl, go for it. H2 gas, CO2 gas, 2 HCl. Yes. Okay, so if this is your reaction, what is the Kc expression? Kc expression. Right. And I always ask you to write the expression first because if you just start plugging in numbers, about once every 3 times, you're probably going to forget to put a number like a squared or a cube or some exponent. It's just because you're so focused on the concentration number you're putting in, you forget to put your exponent. I always write this first, and I've been doing this for a while. So I'm just trying to give you some tips to have some success with this. You have your products squared over each of your reactants to the first. Now you can plug in your numbers. However, we are not given concentrations. What are we given? Moles and liters. Can you get concentration? Oui. Okay, cool. So you can actually plug in the numerator denominator in one little bubble, or you can calculate it first and then plug it in. I'm just going to put the numbers. I don't have my calculator in front of me. So hydrochloric acid, 0.45 moles over 1.25 liters squared over 0.45 moles. I'm sorry, did I do it? Yeah, I did. No, I didn't. I'm sorry, I've got hydrogen listed first. I'm going to do hydrogen first. 0.29 moles over 1.25 liters to the first, and then 0.45 moles over 1.25 liters. And if you are like a parentheses Nazi, you can do this. If not, calculate first and then plug it in. I mean, I track those parentheses like they're my children. I have to make sure that I have them all. So my numerator stays in the numerator, or my denominator stays in the denominator. But your calculator doesn't know what you want it to do unless you put your parentheses in right. Yeah, I mean, I don't know that value right now. I can tell you. I don't have it. Here it is. Any takers?
Wait.
Okay, wait. You can sign language it to me. All right, say first, what is it?
1.55.
Okay, cool. So that's our KC. All right. Peanut Gallery, how would you get KP? It's, okay, so give me the formula.
KP equals KC delta N.
What's to the delta N? The R and T together. Yeah. Parentheses around your R and T. Not just the T, because just the T to the delta N is going to come out to a wrong answer sometimes. To the delta N. Okay, so what is our KP? Don't know. Don't know my KC? Check. What is my R? Okay, well, okay. What's our temperature? It does. It says a specific temperature, a particular temperature. It does not say, let's make up a number. All right, so that's a note to self. Like when a temperature is not given, I can still do the problem. Like Miss Inland did not make a mistake. This is cool. Let's go further. What's the delta N?
Zero.
Right. So I did that as a point to say sometimes you're not going to be given all the data. It's because there's a simpler way to do it. Delta N is moles of product gas over, subtracting moles of reactant gas. And that's a 1 plus a 1. So that's 2. That's 2. So 2 minus 2 is 0. So therefore, your Kp is equal to Kc to the R, or times RT to the 0. And so that's, that's 1. So then now what happens? Great. Very rarely, well not very rarely, the only time you can say Kp equals K equals Kc is when you have what? Same number of moles, right. When will Kp be bigger than Kc? More moles of gas on the product side or reactant side? Product side, because you have to have a positive number to be your delta N. Delta N is a positive number, so you'll have more products minus less reactant moles of gas, and this is all moles of gas. I'm not saying it, but it's there, okay? So if you have more product moles of gas, it means they're going to be causing more pressure for one, but you'll have a positive number here, and then you apply that positive number there, it'll correlate with a higher number for Kp. And then opposite for Kp being less than Kc. So sometimes there's like simple questions that are not actually calculation based, but they're qualitative, quantitative. Then you kind of have to rationalize that in your head. All right, take a quick break. Just a break because I've been talking to you for 40 minutes. You have to move around, jumping jacks, whatever you need.
Did you ever see the video of Kelly of the picture of a mole that we found in Jordan's sidewalk? Abby's. Jordan found it. Abby's sidewalk. I sent it through Sally to you. It was a while ago. I think I still have it too.
Why do I have a picture of a mole?
Oh
my gosh, I swear. People change my SAT word all the day. It was ominous.
Oh. Did you erase the sentence? Really?
Alright, what do you
Sarah Ferris, I don't have it.
Okay, I'll show it to you.
Okay. Hold on, I gotta pull up the stuff. The reason I took a break was because for me too.
I was making something, I'm making something. You don't
Lots of things.
Oh. This one, I have the outline.
I don't know.
Hold at your desk, I'll get it in a second.
Disappeared. It's no longer there.
I'll see it.
It's gone. Oh, there it is.
Ew!
What is it? Is it a mole?
It's a mole.
I think it's a bowl. Why are you saying it's a bowl? Poor mole. Why
Is it live?
Animal.
Because I thought you would appreciate that it was a mole.
Dad, it goes live.
That's sad.
My cat. It was just like hard. It's in our sidewalk.
Oh my god.
All the time.
I'm good.
It had like cheese marks in it and everything. Like I like rolled it over.
Wait, it's
You're like,
Okay, minute up. Okay, I'm gonna count you off. You ready? You're going to be in threes. This is a quick.
Wait. I'm not good at this.
1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, if you have it, you're one.
It's okay.
If you are in the 1 group, you are going to calculate the K of experiment 1. If you're in the 2 group, you're going to calculate the K for experiment 2, etc. Okay, so here is the reaction. 2HI equilibrates to H2 plus I2. Equilibrates is a good word. If you need, I'm going to let you write down your reaction first. And these numbers are hard to see, so you can't see. I'm going to say it out loud. Did you write down the reactions? Okie dokie. So.
No. Oh, wait a minute. Go back up.
No.
Is that you know when
Equilibrates?
No, it's not.
Oh.
Yeah. Or was that?
Okay. H2 plus I2. There you go.
Okay. I just forgot.
Right.
What was number 2?
So that is the reaction for all of you. This is experiment 1 data, experiment 2 data, experiment 3 data.
Wait, we scroll back up just a little bit.
Oh. Why?
Because I need to see the other numbers. I was writing down the equation.
Oh no, these are the numbers.
These
See?
are the only, but it was like it said experiment 3.
I'm telling you what we start with of each. Don't worry about it.
Yeah.
The starting points don't matter.
Oh.
I want you to look at the.
Oh.
I want you to get. Look, why the starting points don't matter because you're plugging in equilibrium values. Where does equilibrium occur? What does the graph look like when equilibrium has occurred? Okay, it's
stagnant.
It's stagnant or static or not changing or whatever you want to say. It's when it flatlines. Okay, I don't care what you start with. That's meaningless. I mean, it's not meaningless, but it doesn't mean anything to
double check. Okay, I knew that actually. Did you? No.
Yes.
You knew nothing.
It's okay.
Don't pop me.
Is this a lab?
No. You are calculating this right now, like in the next 30 seconds. I need a number. What are you guys doing? Somebody calculate. Oh my god.
Then why you signed this?
Yeah, because I want everybody to give me a number.
Do you really have this? I hope so. I hope so too, Abby. Sometimes I worry about you.
Did you get it right?
Yeah.
But it only gives you one number.
She's greater.
Oh, okay.
Wow.
I got it.
Okay.
I just realized.
But yeah, I mean, you got smart enough to realize that we squared. Like then point over 1.573 squared.
All right, raise your hand if this is your equilibrium expression. Raise your hand if this is your equilibrium expression.
No.
What's wrong? Thank you. Thank you.
That's not right.
All right, guys, come back to me. Come back to me. Come back to me. We all have the same reactions. We all have the same equilibrium expression. What is different about all of our experiments?
Our numbers.
Specifically, numbers meaning what?
Concentration.
At
Equilibrium.
okay, so all of our equilibrium concentrations are different. But this is all at the same temperature. What can you assume right now? Thank you. Everybody's KQ is going to be the same. I don't care what numbers, you have infinite number of possibilities you can plug in for the equilibrium numbers, but the K will work out to be the same because it is occurring at the same temperature. So what is your K? Is that okay? Something like that? Okay. Okay, so I got 5-3. So I got, on the first one I got 1853, second one 18336, and the last one 1838. It's very, very, very close. It's not going to be like spot on all the time, but it's going to be very close. So that's just an example of what you can be presented with on a test, for example. Very, very different graphs, and you might have to calculate and then come up to the assumption. The assumption is that, or the conclusion is that the K values will be the same because they're the same temperature, okay? Now, I told you the initial values didn't matter, but in a table, if you had to make an ice table, you would actually need the initial of both of these, products and reactants. change you could find, and then this value here and this value here will be equilibrium and equilibrium. So the change is something you could find. And normally we decide that was x at first, but it's something that we have to talk about in just a minute. Okay. Last thing for yesterday's notes, and then we got to do some practice. This is something called Q. Q is a reaction quotient. Where do you think they got the variable Q from? Quotient. Okay, thank you. So this is going to be something that you can determine from values given where there's no zero given. You have to determine, you must determine Q when you're given concentrations or values where none of them are zero. I'll tell you why in a second. I'm gonna let you guys finish writing that down first too. Is that too far? Is that good? Okay. Let me do some in a second. Alright, I'll come back down to that in just a second. Okay, so the reaction quotient is a number that you're gonna calculate in the same exact setup as you calculate K. So you're still gonna do products concentration over reactant concentrations. But everything we've been doing so far, you're assuming that in my question I'm saying the equilibrium concentration is blah 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 blah. So when it says equilibrium concentration, you plug it into your little setup, but that is going to equal K because it's called the equilibrium constant. Now we're going to do something really similar, but I'm not going to say equilibrium concentration. It's going to say the initial concentrations or the concentrations. Do not assume equilibrium unless it is stated as so. So the initial concentrations just might be like, I threw some apples and oranges in a bag and I'm going to wait and see what happens, okay? But I don't know if I'm going to form more apples or form more oranges or whatever I'm doing. I need to know, am I going to be shifting or reacting up my reactants to form products or vice versa? Because it is a reversible reaction, so you have to figure that out first. And the way you figure it out is because the values that I'm speaking of right now are going to be the initial values. Everything we've been doing before was equilibrium values. That's what we have the IC what we usually refer to for stuff like this. So if you calculate your Q with the numbers that are given to you, and you find in the K value itself will always be given to you, or you will have previously calculated it. If you find that your Q and K are equal, then you are saying that this reaction has the same concentrations as it does at equilibrium. So I'm going to assume it's at equilibrium. That one's pretty simple, okay? So that's that they're equal. But if you have a Q value that's way larger, and you know that Q is still calculated in a similar fashion as K, concentration of products over concentration of reactants, that means how does Q become large? Is this number large, or is this number large? Or too large? Right. If you got a huge Q, because Q is greater than K, then your product number is huge. That means you have way too many products, so you need to get rid of some of the products. How do you get rid of the products? You make more reactants. Okay, so I don't say shift left or shift right as much, because those terms are terminologies reserved for Le Chatelier's principle. We say proceeds left or proceeds right. Okay, it's very different lingo, and it means something different. So the system proceeds to the left because you have your reactants, you have your products. In order to consume products, you have to go in the reverse direction. So you're going to be proceeding left. What does that mean for us on this ice table? I'm going to draw an ice table here because Nick is listening. Maybe. Okay. So if you have a number here and a number here and you're going to be proceeding left, it means you're going to subtract x or some number from the product side and you're adding it to the reactants. Okay? Does that make sense? Yeah. Somebody? Okay. So then you'll have some number minus x because you consumed products and then some number plus x because you added reactants. And you do not have to memorize this yet again. If you mathematically make that logic sense, that too big of Q means too many numerators. Numerators represents products. It means you need to get rid of products. It means you need to go the other direction. Okay. Opposite story. Q is too little. You need Q. You need to make more of something to finally meet up to K. What am I too few of? What do I have too few of? Products, right. So in this case, my reactant number is too large. I need to get rid of reactants, so I need to proceed right. When I proceed right, I make more products. Eventually, my product concentration increases, my reactant concentration decreases, and I will come to equilibrium. But when I do my icebox, in this case, it's a normal icebox, or before, during, and after box, where you subtract from the reactant side, you add to the product side. So this one, you're going to subtract from reactants, and you're going to add to products. Good here? Okay, I'll let you guys finish writing that one down. Okay. What's next in your notes? You will type it here. So I'm gonna see if you guys can. I don't think you guys can do this on here yet. You're not knowledgeable enough. I need to show you ice boxes right now. Rice boxes. Okay, I'm skipping this for now. Looks like a lot. Okay, this table, we're gonna fill this out together. It's in your notes. Okay, it's the next page over. Sorry today for me talking a lot and you sitting a lot. I don't like to do that much, but let me do it for today. Alright, so I'm going to show you about how to calculate the equilibrium constant K from an ice box now. So we've been talking about it, now we're finally actually going to do it. So, our ice tables, ice box, how are we going to say it? So if you have a reaction, you can set up your K expression, yep. If I give you equilibrium concentrations, you can plug it in and find the K value, right? Okay, but now I want to see if you can actually get your own equilibrium values to then plug in. So if I give you a reaction like this, first of all, let's just practice one. Considering this reaction, our K value is 0.5. In which direction will the reaction proceed if we start with the following conditions? All of them are equal. How are you going to figure it out? I don't think this is like your notes. This is just us.
No, it's not what it is.
It is? Okay. How am I going to figure this out? Plug it into what? Okay, what is, well, I know my KC, but what the KC expression that you're talking about, am I going to be calculating K or something else? I'm going to be calculating Q, right. Okay, because anytime you're being asked for a direction of a reaction being proceeding, pretty much that means, in your mind, compare Q and K. We have K, we need to get Q. It is calculated the same way, you are exactly right, but I want you to associate that with finding Q. Because if you say in an FRQ example, find KP, you won't get the point. You have to say find Q, or reaction quotient, whatever you want to call it. So what is the KC expression, or what is the expression associated?
Oh, you want me to tell you?
You know? And then you just plug in your values, and all these happen to be the same. So we'll have 0.1 molar squared, 0.1 molar over 0.1 molar squared. No calculator. Thank you. You see that if you write it out, you'll see those two cancel. So that value is 0.1. I accidentally just wrote Kc. I said write the Kc expression, but this right here is not at equilibrium because it does not say it, so we have calculated the what? Q. Okay. Now, is Q greater or less than K? Less. Okay, so we just found out Q is less than K. What do we need to make more of? Products. We need to raise Q's value up to the point of K, because right now it's too low. So to raise it up, we need to raise the numerator number, which is the product number. All the dots are connected, yes? Okay, good. So we need to make more products. So which way will it proceed? Right. Proceed right. I can't put R because it makes react. Proceed right. Okay, how would you do the next one? I'm not going to do it. How?
You would use
Use the Q equation.
And do the moles over liters for each one.
Right, you would calculate your own molarities with Q over moles over liters. And then, assuming then you would assume the other one is 0. And in this case, NO is 0, so you can't subtract something from nothing, so which way does it have to proceed? It has to proceed right. Because if you proceed to the left, if this is given a 0 because it's not listed here as you can see, if that's assumed to be 0, then you can't subtract something from nothing, so you can't go this way, you have to go that way. So that one, you have to do. I think that's what I have to do there. Okay. This is the one I actually wanted to get to for rice boxes, ice boxes, whatever you want to call them. Okay, so forgive me, I have to talk to you how this works out, but if our reaction is A plus 2B yields or equilibrates to C, and you're given initial, because this is time 0, initial concentrations to be 0.2, 0.25, and then nothing, that to me means I have nothing of C, I have 0 of C. All right, so which way does this have to proceed? Right, okay, correct. It does have to proceed right. The change, this D means delta, which means change. That's your I, C, so that's our change component. And this final part at time 20, we're going to call that E for us, that equilibrium. So next to that or on top of that, put E. Okay, so this is just a subtraction and addition problem. How do I get from A initial to be 0.2 down to equilibrium 0.15? So I'm subtracting X, but I know X to be what? 0.05, thank you. Okay, so I'm subtracting 0.05. That is X. How many X's do I need to subtract from the B column? Right, because of my coefficient of 2. This is a stoichiometric relationship, a 1 to 2 ratio. So this is going to be subtracting theoretically 2 X's, but I know what X is because I can mathematically figure this out. So what is the number I'm subtracting here? 0.100. So do that math for me. You got this, I believe. 0.150. Okay. So then adding or subtracting from C? Adding how many C's? I mean, how many X's, right? We're adding 1 X here because of the coefficient of 1. And usually my BC is right on top of the box. Sorry, it's kind of shifted over there, but you can do it yourself. I'm adding 0.050, so we have a concentration of 0.50 molar. Cool. So these would be considered my equilibrium values. That is what I would plug into the K expression to find equilibrium constant.
What's the relevance of the rest of the chart?
I'm going to show you.
Okay.
So we're going to do ice again. But now I'm going to pretend that my reaction has met equilibrium, and then I do a change. I make some sort of change. I don't know what the change is, but I'm making a change. So now I'm going to start initial with the values I just got. So I just put a little scratch to my E, but you don't have to put a scratch. You just put an I out to the side of it. Normally you don't build ice boxes on top of each other. Usually you do it one time and you're done, but I just want to do it again just to get the hang of it. Delta is C, and then my new equilibrium will be at the 40 number. All right, so I'm starting with 0.50. Notice I don't know my change. I don't see any changes here. I don't even have reactants down to my equilibrium values, but I do see that I have now 0.075 of C. What was my change? Right, I changed it by 1x because of coefficient of 1, so x was point what? 0.025 molar. Okay. What were my x's over here that I changed previously? Like, you know that I'm adding x over there, okay? Okay, and then I don't have a c value. Okay. So I'm going to minus x here because my a had a coefficient of 1. I'm going to minus 2x here because I have a coefficient of 2 here. And this is me assuming we're still proceeding right. I don't have the k value to compare this to, but if I wanted to, I could have made you guys take those values and calculate q compare it to K to figure out if we're going to be proceeding right or proceeding left for the subtraction values, but I just don't have the K value established. Yeah.
If you calculate Q and K the same way, how do you get different numbers?
If the formula is the same, but the numbers inside will be different. Because the K expression values are the true values at equilibrium. The Q are just some random numbers. You're like, I don't know if it's at equilibrium or not. You've got to compare. And if it's too big, then it's not equilibrium. If it's too small, it's not equilibrium. Okay, so then you're subtracting 0.025 and then subtracting 0.050. So this is what? Okay, and this is? Okay. All right, let's do it for real problem now. I think you guys got the hang of it. It's mainly the x's, and utilizing x's in an appropriate way should be something you practice. All right, this is on your paper. An equilibrium was established at 500 degrees C. The equilibrium of the following, at equilibrium, the following concentrations were measured. Determine the Kc. How would we do this? I don't think we need to do this. How would we do it? Write the expression, which would be products over reactants. Do I exclude anything? No, they're all gases. They're all to the first power. Cool. Then do it. Right. Why am I blaming specifically those? Because what does it say? At equilibrium. And then you would find Kc. Okay. That was too easy. All right. On your, this is where I need to stop. I think you can do all your calculating equilibrium concentrations. Problem set. The first one, it says at a certain temperature, the reaction below has a K equal to 0.50. You see that one? Mm-hmm. Start there. And let's see if we can do these. You can work together, but I'm going to wait to show you a couple more, because I think we can do this. Oh, biology. I'll grab them. So I'm going to forget they're there. Slow. This computer don't like me. We're going to try these. I do have like 20 lecture problems I can go through, but let me see if we can do this. You guys can see the answers on the bottom too, so. Can you calculate them?
It should be.
Let's stop this video.